Hello everyone, this is Dr. Chen. In this video, we're going to go through the following chemical kinetics question. And more specifically, which of the following reaction mechanism A, B, C, or D is consistent with the rate law? So in order to validate a reaction mechanism, we have to first make sure all the steps in each of the reaction mechanism A, B, or C, and D will add up to the overall reaction. Okay, so what is the overall reaction then? It is this one here. And then the second requirement it must fulfill is the rate law of the proposed reaction mechanism should be consistent with the experimentally determined rate law. Okay, and the experimental determined rate law is given here as rate is equal to rate constant K times concentration of NO2 squared times concentration of O3. So that is my strategy that I'm going to apply to each of the reaction mechanism. So what I have here is I'm adding step 1 and step 2 in reaction mechanism A. N2O4 is intermediate to cancel out, and I have 2 NO2 plus O3, and the product is N2O5, NO2. Okay, so you can see this fits with the overall reaction, so it fits the first criteria, so that's a possibility. Let's move on to reaction mechanism B. NO5 and NO5 cancel, they're intermediate. It is the intermediate, and I will end up with I will end up with the following: NO2 plus O3 plus NO5, and the products are N2O5 plus 5 divided by 2 O2. As you can see, this overall reaction does not match with the overall reaction above that's highlighted here. So B cannot be a possibility because it failed to fit the first criteria, that the steps does not add up to the overall reaction. All right, moving on. NO3 is canceled, and we'll end up with 2 NO2 plus O3, give me N2O5 plus O2. So this add up to the overall reaction, so that's a possibility. And finally, N2O2 cancel, excuse me, N2O2 cancel, you're left with 2 NO2 plus O3, give you N2O5 plus O2. Okay, so this is consistent with the overall reaction. So now we're down to 3 choices. So what I'm going to do next is to write the rate law for reaction mechanism proposed in A, C, and D. So in A, the slow step is the second step. Okay, so I can write the rate law as the following: rate for reaction mechanism A is equal to rate constant at step 2, that's what the subscript 2 is for, times concentration of N2O4 times concentration of O3. However, N2O4, just going to write this in a different color, is an intermediate. And the rate law for the reaction cannot have intermediate. Okay, the rate law for the overall reaction cannot have intermediate. So this is why I'm going to use steady state approximation so that I can express N2O4 in terms of other reactants in which the concentration can be more easily determined. It's quite challenging to figure out the concentration of an intermediate because, as you can see, intermediate is produced in one step and being used up in the subsequent step. So that's why we're using steady state approximation. So I'm going to write below, steady state approximation is the rate of producing N2O4 is the same as the rate of consuming it. Okay, so let's write the rate law that governs production of N2O4. We can see N2O4 is made in step number 1. So step number 1 is this step here. It made N2O4. So according to that step, I can write the following rate law. Rate of production of N2O4 is equal to rate constant for step number 1 times concentration of NO2 times concentration of NO2. But instead of writing NO2 times NO2, I'm going to write it as NO2 squared. Is equal to the rate of consumption of N2O4. So the steps that use up N2O4 is step number 2. Okay, so we can write the rate law for that reaction as the following. K2, rate constant for step number 2, times concentration of N2O4 times concentration of O3. Now we have that, we can isolate for N2O4. So concentration of N2O4 is equal to K1 times NO2 squared divided by K2 times O3. So this is my new expression that allow me to calculate N2O4 in terms of other concentration of the reactants that can be more easily determined. So all I have to do right now is to substitute this amount or this expression back to the original rate law for reaction mechanism proposed in A. Okay, so now what we have is the following. Rate is equal to K2. Instead of writing concentration of N2O4, I'm going to write this new expression. K1 times NO2 squared divided by K2 times O3. And then multiply by O3. Okay, so this is my new rate law that I use the expression that I derive in the square box here. So let's cancel some terms here. K2 cancel with K2, concentration of O3 cancel with concentration of O3. So the rate law for reaction mechanism proposed in A is equal to rate constant K1 times NO2 squared. Okay, and as you can see, this is not consistent with the experimental determined rate law, which says rate is equal to K times concentration of NO2 times concentration of O3. So I'm going to put an X here. It is not consistent with the experimental determined rate law given here. Okay, so A is not a possibility. All right, so let's move on to C. So in C, we can see the slow step is actually the first step right here, which means the rate law for reaction mechanism proposed in C is the same as the rate law in step number 1, the slow step, i.e. the rate determinant step. So for C, I can write the rate law is equal to K1 times concentration of NO2 times concentration of O3. Okay, and we can see that this rate law for reaction mechanism proposed in C is consistent with the experimentally determined rate law here. Rate is equal to K, a rate constant, times concentration of NO2 times O3. Okay, so C is a correct answer. So for the sake of completion, let's move on to D as well. Okay, the slow step in reaction mechanism proposed in D is also the first step. So let's write the rate law. Rate is equal to rate constant for step 1 times NO2 times NO2. I'm just going to write it as NO2 squared. So this is not consistent with the experimental determined rate law, which is given above as K times NO2 times O3. Okay, so that's why the correct answer for this question is C.